Hi, this is Andrew with Eskimo, and I'm very happy to be joined today by Dr. Thrishantha Nanayakkara. He is a senior lecturer at King's College London, specializing in biomedical engineering and robotics. Trish, thank you for being with us today.
Thank you for having me.
So the title of our discussion is Robotic Learning Based on Demonstration. Can you tell me, how does robotic learning based on demonstration work?
Robots they have to be programmed some way to behave. So one way to program them is to show them how something, for example, how to throw a ball, how to use a spoon to do something, how to use a chopstick, let's say, to pick something. So you can show them, and then the robot might pick up some kind of a representation of that behavior. So the biggest problem of demonstrations is, like, we humans demonstrate using our limbs, and they are different from the robot's limbs or hands or the body. So the robot has to do a very complex calculation to relate what we demonstrate to its own frame of reference and their actuators. So basically, learning based on demonstrations involve first watching some demonstration and then extracting what is relevant, task relevant. For example, I can be demonstrating something while scratching my head, and then the robot should know, okay, so that scratching part is not relevant to this demonstration. So that's a very difficult thing for a robot to do. And then there can be things moving around in the environment, and then the robot, how does the robot know that, that thing that moved in the environment is not relevant to the task? So that is the first phase of problem it has to solve. And the second phase is, as I said, to relate my frame of the body frame to its body frame, and then to scale it up and down in various ways, and then to relate it to its body, and then repeating it to test what he did, and then getting feedback. So this is something we try to solve in the European Union funded Darwin project consortium. So King's College is a partner to the consortium of other countries like Italy, Italian Institute of Technology, and so many other partners in Europe. So we try to basically solve this problem of how to learn and the modalities to learn, and then whether it is camera based, or whether kinesthetic demonstrations or any other form of demonstrations. So it's a very difficult task to do right now.
Trish, what is imitation learning and reinforcement learning?
Imitation learning is trying to repeat the same movement profile as it is. For example, if I try to let's say pick up a cup of coffee, the robot might try to do the same thing in the same way, like the same acceleration, velocity, profile, and the height and everything. But reinforcement-based learning is a little different in the sense we give the robot some kind of a reward criteria. So, for example, lift the coffee cup with minimum jerk, right? So minimum vibrations, or smoothly as possible, or minimize your motor torque. Minimize your maximum torque, or maximize stability and things like that. So we just give him some kind of criteria to be achieved, optimized over time, and then the robot comes up with its own strategies, different strategies that will maximize this cost or reward function, or minimize the cost function. So then it might come up with strategies that we never thought of. So that is the basic difference between reinforcement learning and imitation-based learning. Imitation tries to just replicate that behavior without thinking of why we did this, what we did this, and what is the underlying logic or whatever.
What are the limitations in this field currently?
The biggest limitation is the interpretation of demonstrations right now. So, let's say if you use vision, the camera information can have many information, movie background noise, things, irrelevant information, and then how to extract the most relevant information is a big problem. And how to relate the information to its own representation, its capabilities, and its own body structure, the kinematics, and things like that is another problem. The other problems are planning demonstrations, like how should we demonstrate the sequence so that the robot will find it easy to learn. So most often, like when we train a child or somebody that is intelligent, we demonstrate as a sequence, like, okay, so throw the ball, so this is how you reach to the ball. This you hold the ball, this is how you grasp the ball, and then this is how you throw the ball or something like that. So it can be good for an intelligent brain, like a child brain, but for a robot, it may not work. So how to figure out the best way to demonstrate is another big limitation. And then the common basic limitation is computation speed. So a robot has to process a lot of concurrent information coming from different sources. Vision, it's all motors, it's all body sensors, stability sensors, movement sensors, etc. To process them in parallel or concurrency is a big problem. So once we learn something, to replicate it in very unstructured environments is another big problem. So I can demonstrate something, for example, using a cup, but if for a different cup, will the robot be able to generalize it for all the cups? That's another big problem we have to solve in the future. Or if something goes wrong, can it come up with an alternative strategy quickly, or does it have to completely abandon the task? So that kind of error prone, like when to give up, or how to take a decision, how to proceed, or when to give up, and then how to change things is not solved yet.
Thrish, what is the most exciting advancement you've seen in this field?
It is very personal. I think the biggest exciting thing we have seen is in our Darwin project, this so-called European funded Darwin project, is the robot's ability to use tools in different ways. For example, I can use a pen to do various things. I can use a pen to point at something. I can use the pen to write. I can use a pen as a tool to open a door or something sometimes, or even to repair a bicycle. So a robot, they are very limited in this ability to use tools in the environment to achieve things. So we call it affordances of objects. To suit a given environment, how to use things in the environment to achieve some given goal. So the most exciting thing I saw in this project is like the robot's ability to use L-shaped some tool and reoriented it and to pull something towards it that it couldn't achieve without just by reaching. So that kind of usage of tools to augment the environment is a big advancement I saw, because it was simply demonstrated in another way, and then the robot could kind of generalize it and change it and then use it. So that is one big excitement. And then I think in other projects like Cosmos, it is again done by King's College is a partner to that. That is artificial intelligent applications in factory assembly. So that is also, it has a lot of learning based on demonstration applications. And another is another EU project called StiffLop, where we develop a soft robot like an octopus that can squeeze and go into a body, and then it learns based on demonstrations done by a surgeon. So we are seeing some exciting developments where this kind of surgical robots, advanced surgical robots, can learn based on demonstrations given by experts. So these are really rewarding and exciting developments I see here now.
Thrish, thank you once again, and it was a pleasure interviewing you. Thank you.
Thank you very much.